All right, I think if you're ready, Ruth,
I am.
we'll start. So it's my great pleasure to introduce Ruth Durrer. You'll correct me if I'm pronouncing it wrong. I
That's
apologize.
fine.
From the University of Geneva. Ruth has been there for now quite a while. I think close to 2 decades. No, maybe longer. When did you first
Even
arrive?
longer, yeah.
Even
Yeah.
longer, yes. And was there long enough to be forced to have to be director of the theory group for some
Mm.
period, but thankfully was relieved of this and is allowed to do research again. Ruth has a long history of working in cosmology. Among many of her contributions, she literally wrote the book on the CMB for many people trying to learn about it, and has worked extensively previously on cosmic strings and their impact on cosmology. I am not a cosmologist, so I feel like I can't really do your full career justice. So we'll just say you are easily one of the world experts on cosmology. You're going to tell us about it today. So please go ahead.
Thank you for the kind introduction, and thank you for having me to tell you a little bit about the present activities in cosmology. You will see it's a fascinating subject. It's one of the things that I like best about cosmology is that it combines theoretical physics with experiments. We really have amazing experiments, and I cannot do other than also talk a little bit about them, even though this is a theoretical physics audience. But this is also, I think, one of the fascinating aspects in cosmology, that we do have the confrontation with experiment really close. And I will now share my screen. Please interrupt me, ask questions whenever you have, also during the talk. That's absolutely fine. I'm now sharing my screen, and let's see. Let's hope this works. Okay. Do you see my screen?
Yeah, yeah.
Okay, very good. So the topic of this talk is testing general relativity with cosmological observations. So you see already there observations, our way of doing experiments in the universe. We cannot manipulate anything. We just can see what's there and make conclusions from there. So let me see. So the outline of my talk is, after an introduction, I will talk about very large galaxy surveys, because the talk will be mainly about what can we learn from them, what do we actually see. I will talk about the angular power spectrum and the correlation function of galaxy number fluctuations, how they will allow us to measure the so-called lensing potential. And then I will talk about a statistics called the EG statistics, which helps us to test general relativity, and a way how we can measure the growth rate of perturbations, because this is really a good way to test general relativity. And after that, I will conclude. You all know that Einstein's theory has been tested in many ways and passed all the tests with flying colors. We have seen light deflection not only with the solar eclipse experiment of Eddington around the sun, but light deflection has become actually an astrophysical tool to observe and measure masses, what we now call lensing, strong or weak lensing, depending on whether we have just slight deflections of the light beam or whether we see multiple images, etc. This has become a real astrophysical tool. Then the perihelion advance of Mercury, as you all probably have learned at university, and many other binary systems where the perihelion advance is not just 40 arc seconds per century like the one of Mercury, but degrees per year and stuff like that in close binary systems. Shapiro time delay, B modes, you name it. Since about 9 years now, we also routinely directly observed gravitational waves. So you may ask, why do they want to further test general relativity? We have tested it, it's fine. But all these observational tests which we have are actually tests of general relativity at roughly solar system size or smaller. And furthermore, they mainly test the vacuum solution of Einstein's equations. So in cosmology, there are two differences to this. The first, which I find very interesting, is that we would want to test general relativity with a non-trivial right-hand side, with an energy momentum tensor, which is not negligible. And also, we are testing the theory on much larger scales. We know that physics can change if we change scale, right? If we go from human scales to atomic scales, physics changes quite a bit. So maybe it also changes when we go to larger scales. And on very largest scales, the main interaction which is still active is gravity, which on small scales, the size of the CERN experiment or so, is nearly completely negligible. So actually the most prominent solution which we know of Einstein's equation with a non-trivial right-hand side, and of which we have lots of observation, is the cosmological solution. The Friedmann-Lemaitre universe is the assumption that we can neglect spatial dependencies on very large scales, and that the dynamics is given by a so-called scale factor A, which depends only on time. So this solution breaks Lorentz invariance. It has a specific so-called cosmological time with respect to which the hypersurfaces of constant time are spaces of constant curvature. And here we have a right-hand side, which is given by an energy density and the so-called cosmological constant. There is a constraint equation and a dynamical equation which determine the evolution of this scale factor. Now the question is, have we tested this equation with cosmological observations? Do we really know that these equations holds? What have we really observed? On the one hand, we have counted galaxies, light coming from galaxies, and we roughly know how many stars are in a galaxy because we know roughly how much light stars emit. So we can kind of measure the star density, or if we look at X-rays, some of the gas density in the universe. So that would give us kind of rho, the energy density. And have we tested this? How can we look at the left-hand side? What we have done is we have estimated distances by looking at objects, sources, of which we roughly know the absolute luminosity of the source. And we measure the flux at our position. And from that simple law, we can estimate the distance, the luminosity, so-called luminosity distance, because what in flat Minkowskian space is a distance, in cosmology, these distances are different. If we measure distance in this way via the luminosity, or if we measure it via the size of an object projected in the sky, we will get different results. And we understand that has to do with the expansion of the universe. That is very well understood. So if the geometry is the one of such a Friedmann universe, this luminosity distance is given by this integral. The redshift here is just the inverse of the scale factor. It's because if light is emitted, due to the expansion, the wavelength is stretched, coming to us, leading to a redshift really given by the ratio of the present scale factor divided by the scale factor at emission. Usually one sets the present scale factor to 1, so, but that can be done or not be done. So what we have measured is this luminosity distance, and we have inferred from it h, the Hubble constant, so the a dot over a, the rate of expansion, because it's the integral of this Hubble constant. And we have tried to fit this Hubble law with an energy density and a cosmological constant. And what did we get? This is a kind of old plot. I will show you a newer one a bit later, but the results haven't changed. And the nice thing about this plot is that it shows what I want to discuss here. The vertical axis here is kind of the logarithm of the distance, and the horizontal axis is the redshift. And one can calculate what one would expect this relation to be if one has a universe with only matter density. Maybe let me go back. There is one point which I forgot to say. If you look at the second derivative, you see it is always negative if we have positive energy density and pressure, and it can become positive only if lambda is important, or if pressure is very negative. Energy density cannot be negative because of the first equation. You see, this sum here has to be positive, except if curvature is very negative. And that is the observation. So you see, it seems that acceleration is necessary in the at present until about redshift 0.5, and only later a decelerating universe is possible. So this data can be fitted very well with a cosmological constant which contributes about 70%, and matter which contributes about 30% to the expansion rate. The baryons alone contribute at best 4% to the expansion rate. So matter must be dominated by so-called dark matter, and there must be a significant cosmological constant if we want to save general relativity, right? We could also say, okay, this equation, which we wrote down on the previous slide, is completely wrong, and there is no dark matter and no dark energy, but general relativity is wrong. And that's the topic of the present talk. Can we test that? Because in principle, you know, if we have Einstein's equation, if the left-hand side, sorry, for you, I have to wiggle my right-hand side to make you see it on the left hand. If the left-hand side can always be written as G mu nu equals to something, and the right-hand side can be interpreted as energy momentum tensor, which is modified in some way if we have a modified modification of general relativity. So in this sense, it's not easy to test general relativity. On the other hand, energy and momentum from ordinary matter, or from matter as we know it from particle physics, satisfies certain conditions like dominant energy condition or so. It cannot be arbitrary, weird. So if we will find something very, very strange for the so-called energy momentum tensor, we will assume that this hints us to deviation of general relativity. So the plot which I show here presently looks, so yeah, first of all. So we have not really tested the previous equation, but we have postulated the existence of dark matter and the existence of a cosmological constant to save general relativity. So this actually is the reason why many cosmologists say, let us test general relativity. Maybe our, 95% of the content of the universe, which is required to satisfy the so-called Friedmann equations, is not what we have seen directly, what we have observed directly. So maybe the Friedmann equation is wrong and general relativity is wrong, and it's not, and this dark matter and dark energy seem to be there. With dark matter, I think the situation is a bit less dramatic because we have seen it also in galaxies. We have seen the gravitational field of galaxies via the so-called flat rotation curves, via the velocity of objects around it, and also via lensing. And we have measured that this mass is much larger than the mass coming from stars and gas. So there is dark matter in there. We know the existence of dark matter not only from this cosmological expansion law, but also from smaller scales of galaxies or even dwarf galaxies. So their situation is less dramatic. But the cosmological constant, we haven't seen it in any other way than due to the expansion of the universe. And so it would be interesting to test whether this is really a cosmological constant or whether it is something else. The special thing about the cosmological constant is that it does not do any clustering. And that's why clustering is very important. Actually, in this figure, also the 3 red points here, I will come to those later. They are so-called BAO points, baryon acoustic oscillations, and I will explain you what this is a little bit later. This is the present way of this. We see this graph. It's slightly different here. It's the distance modulus, but not minus the one of the best fit universe. So there is a trend. And the inferred matter and cosmological constant density is the same as in the previous plot within error bars. This is from the DES collaboration, 5 years of data. It's the total which you see here is, as you can see, close to 2000 supernovae instead of only about 800. So the data has roughly doubled. And this is going on. It will double again in the next few years. But probably the situation will not change a lot. Supernova are not by themselves standard candles, but they can be standardized via some corrections applied to their light curves. For example, they have broader light curves if they are more luminous, etc. And these kind of corrections have been tested very well. And so the spread of these supernova curves is quite small. The fact that you see here these significant outliers is that in this, the supernova spectra are not measured with very high precision. So one is not entirely sure that all these supernova are type 1a. And so here there is, in addition, the probability of them being type 1a's. They are correspondingly weighted. And you see where you have dark blue, the spread is much less than for the light blue ones, which may actually be different beasts like type 1b supernovae, which are not so well known and do not fall into this category. But anyway, so this data seems, these results seem to be corroborated also with newer data. In this talk, however, I want to focus mainly on on observations of clustering. As you all know, the universe is not perfectly homogeneous and isotropic. There are galaxies, galaxy clusters, voids between them, etc. And this clustering will actually help us to test Einstein's equation to some extent. And I shall do this in this talk only using two-point statistics. You know, if we have a theoretical model of how fluctuations in the universe were generated and evolve, these models usually only give us statistical quantities and not, doesn't tell us in this place there will be a Milky Way galaxy, in this place there will be a void. It will give us some indications about statistics of voids, statistics of galaxies, etc. And what is nice is the most simple inflationary models, which generate quantum fluctuations, which later become the classical fluctuations which we see via squeezing, they generate fluctuations that are to a big extent Gaussian. And if we have a Gaussian fluctuations, the two-point correlations actually tell us everything. However, the nonlinear evolution of gravity will modify Gaussian initial conditions into something non-Gaussian. Nevertheless, on large scales, linear perturbation theory is widely can be applied, and on those scales where the evolution remains linear, fluctuations remain nearly Gaussian. And so looking at two-point quantities is a good first step. It's not sufficient, but it's a good starting point. And that's what I'm going to talk about today. And it's relevant mainly for scales on which linear perturbations can be applied. That's relatively large. Perturbation theory can be applied, which is relatively large scales. As you probably all have seen this picture, this picture, or probably also the curve below it. That's the cosmic microwave background. There we have analyzed it using linear perturbation theory and some interesting corrections to it. And if you compare here the data points with this curve, which has like 5 parameters in it, or 6 parameters, sorry, 6 parameters in it, you see we can explain roughly 2000 points with 6 parameters really well. So we have understood something. And this, what you see here, is the so-called power spectrum of the cosmic microwave background. The temperature fluctuations, since this is data on a sphere, it can be expanded in spherical harmonics. And due to statistical isotropy, these spherical harmonics, the amplitudes of different L's and M's should be uncorrelated. And for a given L, all M's should give the same result for statistical isotropy. And that's the CLs, the CMB power spectrum. And that has been measured with very high accuracy and is in very good agreement with the universe, which contains 70% roughly of cosmological constant and about 30% of matter, and where the initial conditions are Gaussian, simple power law, nearly scale invariant as predicted by inflation. These peaks here, which you see, are actually the so-called acoustic peaks, which we will also measure in the galaxy distribution. They come from the fact that once perturbations enter the horizon, become causally connected, the baryon-photon fluid starts to do acoustic oscillations. These are really exactly like sound waves because there is gravitational attraction which compresses them, and then there is the pressure which expands them. And the CMB now is a photo at the moment of recombination of these oscillations. So some fluctuations are in a compression maximum. This is this first peak. Some are in an expansion minimum. This is the second peak here, because that's the square of the fluctuation. So minima and maxima are maxima here in the square. This is the third peak, etc. Right now, we have measured roughly 9 peaks with statistical significance. And the fact that they have different heights, we also understand, because first of all, there is a damping envelope on small scales in the CMB, and also contraction baryons, due to their weight, amplify contraction and make expansion peaks less shallow, so that we have the second peak much smaller than the first peak, and the third peak roughly the same height as the second. This tells us how many baryons there are in the universe, and this is in excellent agreement with having only about 4% baryons, and the rest some dark matter, dark in the sense it doesn't couple to photons. Now the question is, can we do a similar analysis with galaxy catalogs? Here you see the Sloan Digital Sky Survey. All the dots here are galaxies, and the distance we are sitting here, this dark region is the region which is obscured by the presence of the Milky Way, where we cannot do very statistically complete observations. And these are the observations of the galaxies, which you see, they form a kind of net with voids. And so it's not very clear here, because this is, of course, a two-dimensional projection of three-dimensional data. What we have done so far mainly is we have looked at the galaxy power spectrum. The galaxy power spectrum here at 2 different redshifts is shown, the monopole of it and the so-called quadrupole of this galaxy power spectrum. We don't see, we see an angular dependence, which depends on our direction to the galaxies which we observe, because the redshift of the galaxy is also affected by peculiar motion, by radial motion. So if we see, if we consider this direction, or a galaxy over there further away from our line of sight, this makes a difference. This produces a quadrupole and also an octopole in the galaxy power spectrum. The power spectrum is just the square of the Fourier transform, is just the Fourier transform of the correlation function, or the square of the Fourier transform of the density fluctuations, roughly speaking. But exactly it is the Fourier transform of the correlation function in real space. However, if we want to take fully into account that all our observations are made on our past light cone, which we have to take into account, we don't have a three-dimensional hypersurface of data which we can just Fourier transform. We cannot observe the correlation function on a hypersurface of constant time, but we see it on a light cone. And we see, for example, density fluctuations which are further away from us, further in the past. We cannot observe 3 spatial dimensions, as I said, but we observe 2 spatial and 1 light-like direction. That's the light cone. Or more practical, what we truly observe are 2 angles, namely the direction of a galaxy and its redshift. These are truly the observable quantities. And the measured redshift is perturbed by peculiar velocities, which is partially taken into account in this quadrupole, which I was speaking about just a minute ago, but also by the gravitational potential from the galaxy. And not only the number of galaxies is fluctuating due to density fluctuations, but also the volume is distorted. The angles we are looking into are actually not directly the angles where the photons are emitted into, but they are deflected by the gravitational potential on their way coming to us. For small galaxy catalogs, which go to redshifts much less than 1, these effects are not so important. But when we go out to redshifts 1 and larger, they do become important. And already for the BOSS catalog, which I showed you just in the previous slide, which goes out to redshift about 0.7, this is relevant. Or for DES, which goes out to redshift 0.8. But the future and present surveys like DESI and Euclid, but also the future ones, LSST and SKA or WFIRST, these will be really important and will have to be taken into account. But what I want to explain to you now, this is actually not only an additional difficulty, but it's also something which will help us to test general relativity. In a Friedmann universe, the co-moving distance out to redshift to a given redshift is just the integral of the inverse Hubble parameter, which can be cast in this form if we use the Friedmann equation. That's the matter density in units of the critical density. That's a possible curvature. That's a cosmological constant, or we might have some other matter components. So what I want to show here is only that this result depends on the cosmological model. And the angular diameter distance, if we measure distance by saying, I know the size of an object, if I see it under a given angle, I know how far away it is via just dividing the size by the angle. This gives the angular diameter distance, which in cosmology is given by this expression and differs by a factor 1 plus c squared from the luminosity distance. At small redshifts, when c is small always means redshift much less than 1, all these distances are given by c over h naught. And for this reason, cosmologists use as their unit of distance h to the minus 1 times megaparsec. This h here is not Planck's constant. This is the value of this Hubble constant here in units of 100 kilometers per second per megaparsec. Its value is somewhere between 0.6 and 0.75. We don't know it very well. So a megaparsec is about 3 million light years. This is the typical distance between galaxies. So it's a good unit of length used in cosmology. And so to take this into account, if we measure a redshift, we can immediately give its distance in units of h inverse megaparsec. What we use for that is just the speed of light and nothing else. So as long as c is less than 1, all is fine. We have adapted our unit of length to our uncertainty in the Hubble parameter. But once the distance becomes of order unity, omega matter, omega curvature, or whatever matter content of the universe enters this equation, and we can no longer use this approximation. And the distance truly depends on cosmology. In other words, whenever we measure redshifts and angles and we convert them into a length scale, we make assumptions about the underlying cosmology. So whenever you see a correlation function, here this is the correlation function as a function of the angle. But if you want to go to a power spectrum, you must get the correlation function as a function of scale. Here it's in megaparsec over h. As long as redshift would be really small, that's fine. But if redshift is considerable, like here 0.7, then the result depends on your cosmology, what you assume, for example, for omega matter. And correspondingly, if you see a power spectrum, somebody tells you, I measured this power spectrum, you're sure that that is not true. One cannot measure a power spectrum. One can only measure angles and redshifts, and one can then assume a cosmological model to convert this into a power spectrum. On very large scales, let us think a little bit about what galaxy surveys truly measure if they count galaxies. At linear order, this has been derived some 10 years ago, 10, 15 years ago. So for each galaxy catalog, we measure the directions in 2 angles and the redshift, as we have already said. And then we can count the galaxies in a small solid angle and in a small redshift bin. And we can compare this count with the mean count, with the mean number of galaxies per solid angle at this redshift, and divide it by this mean. This delta here is really a measurable quantity. There is no theory going in. I don't make any assumptions about what the universe is. I can do that with a certain type of galaxies, with all galaxies, with only very luminous galaxies, etc., etc. And I can then take this quantity and determine its correlation function. Assuming statistical isotropy, I know that this quantity here should only depend on the angle between the 2 directions and on the 2 redshifts. So I can average for 2 given redshift bins, I can average over all separations by a given angle, and so obtain an estimator for this correlation function. And that's what people do. And if you calculate within linear perturbation theory this fluctuation, you get that it is first proportional to a density fluctuation, which I call d here. Then there is a term coming from the shift in the redshift due to peculiar velocity, so-called redshift space distortions. This is this green term and this green term. Then there is a term coming from weak lensing, from deflection, and this has 2 parts in it. This factor 2 here comes from the fact that lensing always leads to convergence. So if I have a galaxy here in front, it will converge the angles. So I'm feeling the density to be lower because I think the separation between the 2 galaxies I'm looking at is actually larger than what it is. So this lowers the density of galaxies. On the other hand, I have a competing effect, which is this 5s, sorry for this factor 5, that's just historical reasons, which comes from the fact that due to lensing, galaxies now appear brighter. And since I have a brightness cut in my observations, I cannot observe 2 faint galaxies. Galaxies which would not have made it into my catalog if there would not have been lensing can now make it into my catalog. And this is this factor here. And actually for some, for example, if you have if you only look at brightness fluctuations, these 2 factors exactly cancel. But if you count galaxies, they in general do not cancel, but they can have either sign. The result of 2 minus 5s can have either sign. And that's the weak lensing term. And here we also have a Shapiro time delay term, which has the same prefactor. And we have a so-called integrated Sachs-Wolf effect, and the effect coming from the gravitational potential here, and also here, which comes from the same as this. But the dominant terms are these 3. The others are really much smaller. But they are there if you do the calculation correct. Here you see this redshift space distortion. On large scales, in 2 different redshift bands, on large scales, you see a squeezing, And that comes from the fact that galaxies which are behind you and falling into some other galaxies, they seem to have lower redshift than what they actually have. So if you convert that into a distance, you convert it into a smaller distance. So you see this squeezing here, make it elliptical. And for the ones in front, it's the opposite. So if they fall into this overdensity centered here at 0, then their redshift seems to you to be larger, and you assign to them a larger distance from you than they actually have. On small scales, this is a nonlinear effect called the so-called fingers of God, which comes from the fact that around this overdensity, there are relatively large velocities, and you see the radial component of them, which is spreading out. These are the so-called redshift space distortions. So now what we can do without doing this conversion from redshift into length scale, we can just say, okay, that's also for a given redshift. This is also a function of the sphere. So let me expand it in spherical harmonics. Again, differentials must be uncorrelated if I assume that the process which generated the initial conditions was spatially isotropic. And so I can now also derive a power spectrum, but which depends on two redshifts. And from it, I can, of course, calculate the correlation function, which is just the angular transform here, the CLs times Legendre polynomials. That's easy to see. And if you calculate this angular power spectrum from perturbation theory, you find that if you look at very low redshifts and very small redshift bins, the dominant term is just the density term. That's what people always took into account, and therefore for low redshifts, this is was absolutely correct to neglect all these additional effects which now are present. However, if you go to large redshifts, and especially if you consider large redshift bins, then you suddenly find that, for example, the lensing term here in magenta can be larger. So this lensing magnification term can be larger than the density term, or at least of the same order. So neglecting it is certainly no good approximation anymore, and this has to be taken into account. But it also is an advantage. So what does this lensing allow you? If you can isolate it, it allows you to determine also the gravitational potential. What I didn't maybe tell with any detail is here, D is the density fluctuation, V is the potential for the velocity, so its derivative is this vector V, and phi and psi are the so-called Bardeen potentials. If you have, in general relativity, the scalar degrees of freedom of the metric, there are two scalar degrees of freedom. One of them is exactly the Newtonian potential, this one, while phi is the term in front of the spatial perturbations of the metric. And if there are no significant anisotropic stresses, so if matter is a perfect fluid or a scalar field or so, then these two are equal and equal to the Newtonian potential, but they can be different. So, and what I also didn't say is here I only account for so-called scalar perturbations. The metric can also have vector and tensor perturbations. Vector perturbations are not generated during inflation, but tensor perturbations, gravitational waves, are, and they would also contribute here, but they are much smaller, and so I don't include them here into this formula to not make it too long. So here you can also look at the radial. So you fix L here, for example, L has been fixed to 20, and you can look at the spectrum as a function of C prime for a given redshift. And here the redshift C is the lower limit here. And you see if the redshift is very small, again, you are dominated by the so-called standard terms, which is density and redshift space distortions, where at higher redshifts, the lensing term becomes relevant. And so this should be measurable at sufficiently high redshifts. What we also looked at is if you consider unequal redshifts, you suddenly find that actually they are dominated from by the lensing term correlated with the density term. Here we looked at different bins for example, the Euclid satellite. If you measure, with the measurements of the Euclid satellite, there will be the photometric survey will be split into 10 different bins, redshift bins. And if you look at, for example, bin 1 correlated by bin 1 with bin 1 alone, the local, meaning density and redshift space distortions, really give you the full signal. However, if you look at unequal bins like bin 1 and bin 4, there is still the density term is important, it's this blue line, but the full result feels strongly also the lensing term. Or if you even correlate bin 1 with bin 10, then the local term, density and redshift space distortion, can be completely neglected and the full signal is given by lensing. So we will be able to measure this so-called lensing potential or the convergence kappa, which is this lensing potential is an integral over the gravitational potential with some weighting function. So we can, in principle, determine also the gravitational potential. Here we have made, let me show you the next figure because this one is too busy. Here we have made a Fisher matrix analysis for a Euclid-like photometric survey. And we have studied how well can one measure this lensing term. We have done this in a very simple way by saying, okay, let us assume this lensing term is multiplied by some constant beta. How well can we measure this constant beta? And we have looked at this for different configurations. If we do only 5 bins, considering only autocorrelation of bins, considering autocorrelations and cross correlations, or if we have the same but a 10-bin configuration. And we have seen that most parameters like neutrino mass, Hubble parameter, the amplitude of the fluctuations, for them it's very important to have 10 bins and not only 5 bins. But whether we consider only the autocorrelations or auto and cross correlations is not so important. However, for beta, whether we consider 5 or 10 bins is not so important, but it's very important to consider cross correlations. As we have seen before, only with cross correlations we can isolate the lensing term. But if we do that, we can measure this lensing amplitude with a few % precision as we can measure the other cosmological parameters. So we will be able to measure this with the Euclid satellite, which is now in orbit since more than a year. So soon the first data will be available. We also found that if we neglect this lensing term, what happens is we infer, for example, a neutrino mass. Here the input neutrino mass was 0.06 electron volt, sum of the neutrino masses, which is the maximum allowed by oscillation experiments. If we assume that the lowest neutrino mass is nearly 0, then 0.06 electron volt is the lowest possible sum of the neutrino mass, to which cosmology is quite sensitive. And we have seen if we analyze data neglecting lensing, even if we only consider autocorrelations, we will infer a rather high neutrino mass. Only if we include lensing can we infer the right neutrino mass. And also the Hubble parameter will come out wrong if we analyze, if we neglect lensing in the analysis, even if we only consider autocorrelations. Here the red line is the correct analysis. The gray line is the one considering only autocorrelations and no lensing. And the blue one is considering just that there was no lensing, but considering all correlations. So you see, because what lensing does also, it's kind of smearing out features in the power spectrum. And that's exactly the same what massive neutrinos do due to free streaming. So one could interpret this as a massive neutrino component if one is not careful enough. We have also studied how well can we actually estimate this lensing potential by doing a linear and quadratic estimator on the potential. And we have found that with Euclid, we can get a signal to noise for the lensing potential of on the largest L of order unity, but the summed signal to noise for all L's will be of order 35 or so. So we will be totally able to measure this lensing potential in this way. The lensing potential is, of course, also estimated by weak lensing measurements, by measuring shapes of galaxies. There we have the problem of intrinsic alignment. These shapes are aligned not only due to foreground lensing, but also due to the intrinsic way how galaxies form. So this has to be modeled, and this is a nonlinear process which is difficult to model with high precision. So the nice thing is that counting galaxies is a new way of measuring this lensing potential, which, as I said, is a weighted integral of the gravitational potential and has different systematic problems. You know, in cosmology, we always want different ways to measure something because we always have systematic problems, systematic errors in our measurements, which are difficult to model. And so to be sure of something, we want to have several ways to see it. Let me come to the EG statistics. Actually, what we can measure is this quantity here, which is the sum of the two body potentials, so twice the gravitational potential, if matter is what we think it is, divided by the velocity. And this, in standard cosmology, with just matter and the cosmological constant, should actually be independent of scale and given by this quantity. This here k-dependent quantity can be converted in a quantity on the sky, because as I said, measuring a length scale always means assuming a cosmology. So k is an inverse length scale. In this quantity, a cosmology has to be assumed, whereas here it has not to be assumed. That's the advantage of this quantity. However, we need to get the density fluctuations and the correlation of kappa and the density fluctuations. However, what we measure is the fluctuation in counts of galaxies. And as we have seen before, this contains a lot of other terms, and that has to be taken into account if we want to go from the galaxy fluctuation, which is given more or less by these expressions, if we neglect redshift space distortions and gravitational potential terms, which are much smaller. If we have a relatively large redshift bin, you can imagine that these small redshift fluctuations are then averaged out if we have considerable redshift bins, and the gravitational potential can be calculated to be at least 2 orders of magnitude smaller than the terms included here. These bias factors, however, are important. They relate density fluctuations to galaxy density fluctuations. But in principle, this can be measured. At low redshift, all these corrections are not relevant. Here, for example, this has been used to measure EEG statistics. Here I show you the theoretical deviations from the measured quantity, which neglected the effects I'm talking about, to the true quantities. And you see it's a few percent or less. It's between 1% and 3–4%. And the accuracy of the observation was more like 20%. So it's not so important. However, for the Euclid survey, where one wants to do this again, the error when not including these effects can be of the order up to 40%. So we totally have to include the fact that when we count galaxies, this is not just the density, but also the volume effect due to so-called magnification bias. But this can be taken into account, and if one does it correctly, one can measure these EEG statistics with high accuracy, and it becomes really scale independent. Here you see lines for different redshifts. Another way to measure these EEG statistics where these lensing magnification terms would be completely absent would be so-called intensity mappings. We plan to measure just the intensity of the Lyman alpha, of the 21 centimeter line, which comes from hydrogen spin flip transitions, to measure, the hydrogen density. So this would measure us kind of the galaxy, the light intensity coming from galaxies without actually seeing or identifying these galaxies. So we can do much fainter observations in this way. And several surveys are now underway to try to measure this. So far, they could see it only in correlation with galaxy number surveys, but they couldn't yet see it independently with high significance. But this will come in the next few years. Another measurement, which is one of the key measurements which Euclid will do, is the so-called growth rate of perturbations. This is very sensitive to the theory of gravity, since a cosmological constant is actually the only form of dark energy which exhibits absolutely no clustering. If we have a scalar field or some modifications of gravity, usually clustering is modified significantly. And the redshift space distortions are very sensitive to this growth rate. So one needs a so-called spectroscopic survey, a survey which measures redshifts very accurately to see these redshift space distortions with high accuracy. Usually lensing convergence is not so relevant in measuring the standard perturbation, cosmological parameters in a spectroscopic survey, but it does significantly affect the growth rate, as you see here. This is the growth rate in SKA2, which will be the square kilometer array, which will count many galaxies and which will be very useful to measure the growth rate. And if we don't include lensing, we will make a systematic error of the order of 1 sigma and more at redshifts above 1. So if we don't take these lensing into account, we will say we have seen modifications of gravity where we actually haven't seen them, where we just made the wrong analysis. So this has to be taken into account absolutely in this analysis. And it's another way of saying we will see this gravitational potential. Now, before I conclude, let me just show you a little bit the first year analysis of the baryon acoustic oscillation from DESI. DESI is a spectroscopic survey. It's the first stage, so-called stage 4 galaxy survey, which has put out results now this year. And they made the ansatz that W is some constant plus some redshift dependence, kind of the first term in a Taylor series. Let's hope that's sufficient for the time being. So you see, W is the ratio between pressure and density. For a cosmological constant, this value is equal to -1 and constant. So if we would find W is equal to -1, this is this line, this would mean we have a cosmological constant. These lines which I show here are the best fits from DESI. And if I wouldn't have this dashed line, I would say, wow, that's not lambda CDM. We see something else here. But you know, the blue bars here are the 1 sigma error bars around these curves, roughly. And so you see a cosmological constant is still in kind of reasonable agreement with it. Nevertheless, the best fits all go below 1 at roughly 0.5 or 0.6. Yeah, 0.6, 0.7. Below 1 would mean phantom, would mean a pressure which is more negative than the energy density is positive. We don't know of any reasonable matter doing something like that. So this might, for me, this would be a hint of modified gravity if we would see this so-called phantom behavior, that we have a W which is less than -1. But, you know, errors in cosmology are to be taken with a grain of salt, and there is 1 sigma evidence for it. So 1 sigma is nothing, right? We need 5 sigma before we believe anything. So, but anyway, DESI data is coming in. These error bars will be shrinking during the next few years. So have a look to this. And Euclid is going to be quite a bit better than DESI. So we will see what's going to happen here. Okay, let me come to the conclusion. Maybe something which I want you to take away from this talk is, whenever we measure correlation function on a hypersurface of constant time, or the power spectrum, or the bispectrum, or whatever, these quantities, they are easier to measure to some extent, or to infer, but they require a fiducial input cosmology, which depends on cosmological parameters. And furthermore, it's not evident how to correctly include lensing in such a power spectrum or measurement, because lensing is an integral along the line of sight. I cannot measure the lensing out to arbitrary positions, only the lensing out along the light cone. I don't know how I would have to do this. I don't know what it is, because there are no light rays going elsewhere than on the light cone. And for future large and precise catalogs, we will be able to measure angular correlation function as functions of redshifts and the angular power spectrum and bispectrum from the data. These quantities will be more noisy, but they also contain much more information. They contain information about the matter density, about redshift space distortions. These two we have already measured and used to infer the growth rate. But what is new, we will also be able to measure the geometry, the space-time geometry, via the effects of lensing magnification. We can therefore, in principle, determine both the components of the energy momentum tensor and the geometry, which will allow us to test Einstein's equation. Especially as we have seen, observing the lensing magnification and the galaxy density is suitable to test GR via the EG statistics, or we can test GR via the growth rate, but it's always important to include lensing, or what people call it magnification bias, in doing so. The spectra which we determine with counting galaxies are these, the so-called shear spectra, or kappa and shear spectra, which are measured by measuring shapes. They depend sensitively and in different ways on the theory of gravity, on the growth factor, on the relation between the two Bodin potentials, on the matter and baryon content, and on the velocity. So they provide us a new route to not only estimate cosmological parameters, which the CMB has done a very good job already to do, but also to test general relativity on cosmological scales. Thank you.
Thank you so much. Are there any questions from the audience? I have one. It's been a while since I thought about this, but I would have thought if W is less than -1, this leads to instabilities, right?
Yes, in the matter sector. That's
Yeah.
why I think this shouldn't be just some dark matter doing this. But however, if you have modified gravity, some Horndeski scalar tensor gravity,
I see.
you can get W less than 1, even in theories which are absolutely stable. So that's why I think if W is really less than 1, this will hint us to modified gravity.
I see.
Also another quantity, like if the two Bodin potentials are not equal, I would also favor modified gravity, because we don't have, I mean, if we have free streaming particles like neutrinos, they generate anisotropic stresses, but we know roughly how much they contribute, and it's very little.
What's the time frame, and how much do you expect the error bars from these BAO observations to shrink? I mean, is this in 10 years, it'll be at 3 sigma, or if it
I
shrinks,
would
it
say
declines?
I would say within 5 years we are at 3 sigma.
Really? Okay.
Yeah. I mean, there is Euclid also on the way. I mean, the first year data, there are problems, like there are always problems if you have a satellite. And we are right now, unfortunately, we have very high solar activity, which perturbs us with cosmic rays and all these things, which I never knew before I got a little bit involved in one of these experiments. But we will overcome these difficulties. I mean, we, the observers, not me, will be able to, yeah. But this is certainly, these error bars will certainly shrink by at least a factor 3.
I see.
Within the next 5 years, would be my guess.
Very interesting.
But, you know, it may very well be that also the lines change their position.
Of course, yeah.
Yeah.
Are there any other questions from the audience?
Okay, I have some question about the Hubble tangent. So in the Hubble parameter measurement, there is based on this variable stars or supernova for very small z redshift, while the one based on the CMB is very, very large z. So that that should really depend on the model like lambda CDM.
Yes.
So it seems that you are emphasizing the clustering of the galaxies. Somehow it will give some probe for general relativity, and that seems to be covering from small z to somewhat reasonably large z equal order of 1. So your data, is it preferring some CMB data or some near the star-based on data, or what can we say?
Very good question. I didn't mention the Hubble tension in my talk, which is probably an exception you would have expected me to talk about. But let me say you the following. The Hubble parameter has also been measured by these BAOs in galaxy surveys, and it is in agreement with the results from the CMB in the BOSS data from redshift 0.3, 0.6. It is in agreement with the CMB, but not with the SHOES or Pantheon Plus result. So the CMB gives typically a Hubble constant of about 67, 68, while SHOES, so supernova and low redshift measurements, give a Hubble constant according to the SHOES project of about 73. And the discrepancy between the two error bars are small enough to make this discrepancy 5 sigma. Here, just I repeat the problem of the Hubble tension for people who might not be familiar with it. Now, I don't know whether you have seen this recent work by Wendy Friedman, where she uses 3 different standard candles to calibrate the supernovae. And she gets also a Hubble constant in the region of 67 to 70, so more or less in agreement with the CMB, while Rees et al. Get a Hubble constant of 73. So these are experts, both groups are the world experts on the nearby Hubble constant, and they agree roughly with the discrepancy which we have. So for me, this is a problem of calibration, because they get different calibrations on the Cepheids, on the tip of the red giant branch, on the J stars. They get difference in the calibration because Rees et al. They also repeated the Friedman work and reproduced their Hubble constant of 74. So to me, this is really a problem of the local calibration, which seems to be, once you are at the supernova stage, once you agree with the distance onto let's say, the coma cluster, out to the coma cluster, you're kind of safe. But so there are at least 1 to 2 papers per day on this Hubble tension, trying to explain it by modifying the physics with some early dark energy or whatever. Of course, the Hubble parameter inferred from the CMB needs the knowledge of where these acoustic oscillations peak. And to know that, we assume that the universe before recombination was dominated by radiation and dark matter later, and there was nothing else. If there was before recombination a period of dark energy, this intrinsic length scale which we need to fix the baryon acoustic oscillations can be changed, and one can get another Hubble constant. However, this then usually spoils other cosmological parameters. For example, it usually makes the so-called S8 tension, which I also didn't talk about, worse. And to fix that one, you have to include another modification, like interacting dark energy, dark matter, etc., etc. It may be that there is something, but I'm not sure. I'm not totally, I'm not working on this because I think it's a problem of the local calibration. If the experts in the field, like Wendy Friedman and Adam Rees, cannot agree upon, I'm sure they are both groups doing their best, cannot agree upon the local distance anchors, then I don't know.
Okay, thank you.
Thank you.
All right. Are there any further questions?
I have elementary question. I think I didn't understand Yeah, how to test the general relativity? I mean, besides the energy momentum tensor, particularly by EG statistics. So will you explain again? Sorry. Yeah.
So explain again what the EG statistics is doing. I
I
can
still
just,
didn't
it's
understand
just
how
like
to
this.
how to test the general relativity, not the
Mhm.
the content. I mean, changing
Yeah.
other parameters. Yeah.
Yeah. You see, in general relativity, we know that, let me go back to the expression for EG here. In general relativity, we know that this sum of the two body potentials is proportional to V times the Hubble parameter, that this is proportional to V. For this, we use more or less the Poisson equation and the continuity equation to get this ratio. So we can calculate this. And we find that within general relativity, it has this form. Now, of course, if you, maybe I'm exaggerating, I should say, within lambda CDM cosmology. But if you add some other, if you have some other dark energy, it doesn't change significantly at all. But if you modify gravity, then first of all, these two body potentials no longer have to be both equal to the gravitational potential. They can be different. And the Poisson equation need no longer hold. For example, if you modify the Poisson equation with some prefactor which depends on scale, which many people do as some kind of effective modeling of modified gravity theories, one actually finds that many scalar tensor theories give you effectively something like that. You suddenly find that this quantity here no longer only depends on redshift, but also depends on scale, on K. And if that's the case, you should see, instead of such a horizontal line, something which depends here, which is scale dependent, like this or like that. If you see something like that, then this means really that, for example, the Poisson equation is violated on the cosmological scales. Does that answer your question?
Yes, you are answering exactly. But is there any other option? I mean, for example, changing ansatz of metric ansatz or slightly, or I'm not sure. I don't know. Yeah.
Okay, this is within linear perturbation theory upon a Friedman universe. But you know, at least the isotropy of the universe is very well observed with the CMB. Now the question is it also the homogeneity? That's more difficult. But if we assume that we are not special observers and also other observers see an isotropic CMB, then we are fine. You cannot have isotropy around more than one point if you don't have homogeneity. But we could have isotropy only around us, and we would be in the center of a so-called Lemaitre-Tolman bonded geometry. That's also a possibility with small perturbations. But people have looked at that, and it's very difficult to reconcile this with observations with a significant radial dependence, a radial dependence such that you could, for example, get rid of the cosmological constant. If you want to do that, you need to have clusters moving at much too large velocities, faraway clusters, which we don't see. So that's already ruled out.
Okay.
And
Thank you.
so I think we are rather certain that the geometry of our universe on large scales is Friedmann-Lemaitre with small perturbations. And that's on which this EG statistics is based. If that's wrong, but I think we can be rather certain that that's not wrong.
Thank you.
You're welcome.
Any other questions? All right, if not, let's thank Professor Durrer again.
Thank you.
Enjoy the rest of your morning, as it's now the evening here.
Yeah,
Thank
enjoy
you
your
again.
evening. Bye-bye.
Bye.